In section 8.5.3, we'll learn how to apply partial fractions when the denominator contains irreducible quadratic factors. We'll consider two cases: distinct quadratic factors and repeated quadratic factors. The overall approach to handling quadratic factors in the denominator will be very similar to the way we set up partial fractions when we had linear factors. So again, in the numerator, we may have a function of x or we may have a constant, but that doesn't drive the way we set up our partial fractions. It's the denominator that determines the partial fractions. So notice in the denominator, we have quadratic factors. That is, x is raised to the power of 2. These quadratic factors will not be factorable. If we could factor them, then we'd be dealing with the case of linear factors. So we are assuming that these are irreducible quadratic factors. For the general format here, the way that we are distinguishing one factor from the next is using the subscripts on the coefficients a, b, and c. A, b, and c represent real numbers. So a sub 1, b sub 1, c sub 1, those are distinct and different from a sub 2, b sub 2, and c sub 2. So that's simply how we, in general, distinguish unique quadratic factors. Now, for each quadratic factor in the denominator, we'll need to set up a partial fraction. So notice my first irreducible quadratic factor here looks like this. That's going to be my first denominator. The second irreducible quadratic factor, if I have another one, that's going to require another partial fraction. And we're going to repeat this for however many quadratic factors we have in the denominator. Now, the way we assign the numerator for a quadratic factor is different than what we did for a linear factor. Notice if I have a degree 2 denominator, I'm going to need a degree 1 numerator. So I have a linear expression, a sub 1x plus b sub 1, for the numerator. So every quadratic factor will have a linear numerator. Remember, if we had a linear denominator, we had a constant in the numerator. So the rule of thumb in general is when you're setting up partial fractions, the degree of your numerator is 1 less than the degree of your denominator. So in this case, we're going to need a couple of arbitrary coefficients, a sub 1 and b sub 1. Same thing will be true for our other partial fractions. We subscript those fractions for the general format, but in practice, it's a little easier to avoid the subscripts and use a, b, c, d, so on and so forth. Okay, are you ready to give this a try? Let's try the integral of 3 over x times x squared plus 4 dx. This is a seemingly simple rational function, but notice it will not fit any of the categories that we've studied up to this point. So looking at the denominator, it is in factored form. We have a unique linear factor, and then we have an irreducible quadratic factor that cannot be factored any further over the real numbers. So we're going to take out our integrand. We're going to apply a little algebra to it before we do the calculus. We're going to separate this into two partial fractions. Now I'm using a combination of techniques here. My first factor is linear, so I need a partial fraction for that unique linear factor, and we will assign a constant numerator to go with that linear denominator. Now for my second partial fraction, I'm going to have my irreducible quadratic factor, but it's going to receive a linear numerator. So I'm going to have the general linear expression bx plus c. Notice that's just a polynomial of degree 1 in descending order. We stop when we get to the constant term. Now that we have it successfully separated into a couple of partial fractions, the next part is the same as what we practiced above or in the previous video. We're going to multiply both sides of this equation by the common denominator, which is the product of our two denominators, x times x squared plus 4. On the left side, notice the denominators would cancel, leaving behind just a 3 on the left side. On the right side, we're going to distribute the LCD to both of those factors. In the first one, the x cancels, and we have left behind a times x squared plus 4. In the second one, now be careful here, I'm going to group the numerator bx plus c together in parentheses. Notice the x squared plus 4 would cancel, and we have a leftover x. Now, when we were dealing with unique linear factors, at this point we chose convenient values of x to cause one of the terms to zero out, and we were able to determine the value of our arbitrary constants a, b, and c. I'm going to show you an alternate approach in this case. This is called the method of undetermined coefficients, and you'll see this type of technique again when you get to differential equations. What I'm going to do, instead of choosing x values, I'm just going to go ahead and multiply everything out. Then I'm going to write it as a polynomial in x in descending order. So the highest degree term that we have here is x squared, and I've got two of those terms. So I'm going to combine those two terms. Notice when we factor out the x squared, our coefficient would be a plus b times x squared. Working in descending order, the next highest power of x is x to the power of 1, and then finally our constant term for a. Because we are dealing with an identity equation, we assume that this equation is true for all x, of course, for which the original fractions are defined. So we're going to assume that we have a degree 2 polynomial on the left, even though it doesn't really look like it. So to make these look equivalent, we could say this is 0x squared plus 0x plus 3. So I can see I have a degree 2 polynomial on the left and a degree 2 polynomial on the right. Now with this assumption, then we should be able to observe that the coefficient of x squared on the left is the same as the coefficient of x squared on the right. That is, 0 equals a plus b. Similarly, the coefficient of x on the left should be equal to the coefficient of x on the right. Notice we have found the value of c. c equals 0. And finally, the value of the constant on the left should be equal to the value of the constant term on the right. 3 is equal to 4a. Notice this indicates then that a is equal to 3/4. So we found another constant. Now I can backtrack to this first equation. We can plug in what we found for a, and we can use that to solve for b. So it looks like b should be equal to -3/4. Now we are ready for a little bit of calculus. We can go back to our original problem, the integral of 3 over x times x squared plus 4 dx, and we can now split it into two separate integrals or two separate terms using this as our model. So we're going to have the integral of a we discovered is 3/4 over x, plus b times x, b we discovered is -3/4 times x, plus c, we learned that c is 0, all of this over x squared plus 4. Let's clean this up a little bit and separate it into two individual integrals so we'll know what we're dealing with. So working on that first integral, I'm going to factor out the 3/4 as a coefficient. We simply have integral of 1 over x dx. For the second term, because our constant term goes to 0, we can write this as -3/4 times the integral of x over x squared plus 4 dx. Again, that first integral is very easy to recognize. We have 3/4 times the natural log of the absolute value of x. As for executing our second integral, think about all the techniques that we know, u substitution, relating to our inverse trig functions, and now partial fractions. This one we can handle with an ordinary u substitution. We can let u equal the denominator. Well, how do we know to do that? Because we recognize at least a multiple of du in the numerator. So I can convert this to an integral in terms of u. So we have coefficient -3/4 times the integral of 1 over u, x dx is replaced with 1/2 du. So carrying our first term, we have 3/4 times the natural log of the absolute value of x. Combining constants in our second integral here, we have 3/8 times the integral of 1 over u, which we know is natural log of the absolute value of u. Let's go back and recover our original variable x. So we have minus 3/8 times the natural log of the absolute value of u, which is x squared plus 4 plus c. Now this is an acceptable answer, but if we want to condense it, we may have to be a little bit clever on this one. I'm going to factor out the greatest common factor of 3/4 between these two natural log terms. So notice right here, I'm going to need a coefficient of 1/2. And keep the plus c separate. Then we can take this negative 1/2 into the exponent position, or let's just take 1/2. So we have natural log of the absolute value of x minus natural log of, now with the 1/2 power, we can convert that into a square root, right? And so condensing our logs, we have 3/4 times the natural log of the absolute value of x divided by the square root of x squared plus 4. So that's your most advanced, most concise answer. Again, if you make it this far, I'm cheering for you. I'm happy you figured out the partial fractions, the u substitution, the antiderivative. So that is awesome. But if you really want to refine your skills, go ahead and condense it using logarithms. So let's progress to our last case for partial fractions. In this section, we're going to consider repeated irreducible quadratic factors. Now, here's the big idea. We're going to include one partial fraction for each quadratic factor up to the power of the repeated factor. That is, we're going to handle it the same way we do with repeated linear factors, but we're going to remember that our numerator needs to be linear, that is 1 degree less than the denominator. So on example 4, notice we have a quadratic factor x squared plus 2 that is irreducible over the real numbers. And also notice it is a repeated factor. We have x squared plus 2 squared. So we're going to take our radicand out. We're going to operate on it a little bit, and then we'll come back and do the calculus. So we're going to need a partial fraction for each ascending power of that irreducible quadratic factor up to the highest power. Okay, that was a mouthful. What does it mean? Well, I'm going to take x squared plus 2 to the power of 1. Now, because it's a degree 2 denominator, I'm going to assign it a degree 1 polynomial with general coefficients in the numerator. Let me use b. b comes after a, right? Now, because it's a repeated factor, we're going to need another partial fraction with that factor squared. And by the way, if x squared plus 2 was cubed, we would have one more partial fraction with x squared plus 2 cubed. Now, we do have there a degree 4 denominator, but because we're dealing with repeated quadratic factors, we only need a linear numerator. So we're going to call that cx plus d. Now, the setup is really important. I have to get my model right in order to find the correct expansion of my original integrand. Okay, I'm going to multiply both sides like we always do by our common denominator, which is x squared plus 2 squared. On the left side, the denominator cancels, and we end up with x squared plus x plus 2. On the right side, we'll distribute to each term. When we distribute to that first term, one of those factors cancels, and we end up with x squared plus 2 left. When we distribute to the second factor, both factors cancel, and we just end up with cx plus d. So again, I'm going to use this new process of multiplying everything out over here on the right side. You may want to go back and compare this to how we did it differently with our linear factors. Remember, with linear factors, we were choosing convenient values of x, which caused some of our terms to cancel. Because we're dealing with quadratic factors here, that's not as convenient. So we're going to multiply everything out. I'm just using FOIL here. And then I can just drop parentheses here on my last term. And then I'm going to rewrite the right side as a polynomial in x in descending order. So my highest powered term is x cubed. Then my next highest powered term, we have bx squared. Notice we have a couple of x terms, so I'm going to factor out the x and combine coefficients. 2a plus c times x. And then also notice we have a couple of constant terms. Now, I'm going to group those in parentheses to remember that those together represent the constant term. Then, because this is an identity equation, we're going to assume that the polynomial on the left is equivalent to the polynomial on the right. Clearly, the polynomial on the right is degree 3, so we can imagine this as having a 0x cubed attached to it. Then we're going to set our unknown coefficients equal, or our corresponding coefficients equal. So the coefficient of x cubed on the left should be equal to the coefficient of x cubed on the right. So 0 is equal to a. So that's going to eliminate this term right here. Looking at the coefficient of x squared on the left, clearly it is 1. We're going to set that equal to the coefficient of x squared on the right, and so we can see b will be equal to 1. Next, we have the coefficient of x on the left, which is 1. I'm going to set it equal to the coefficient of x on the right. That's 2a plus c. Now, remember, back over here, we learned that a is 0, so we can also see here c is going to be equal to 1. And then finally, our constant term on the left is equal to the constant term on the right. And remember, we learned just a minute ago that b is 1. So we can use that to solve for d, and d equals 0. You're going to love it when you get all those zeros. Okay, we are done with the algebra. Let's go ahead and go back to our original problem, which was to find the definite integral from 0 to 1 of this big fraction. We're going to go ahead and expand that fraction according to this model. So we have the integral from 0 to 1. Remember, we figured out that a was equal to 0, b is equal to 1. So my first term is going to look like 1 over x squared plus 2. Second, we're going to add this to, remember, we discovered c is 0, d is 0, c is 1. So plugging 1 in for c, we have x over x squared plus 2 quantity squared dx. We can split this into two separate integrals, which we'll likely have to handle with two different techniques. So I'm going to split it up here. Now, believe it or not, we can integrate that first term directly. Do you notice that we have the sum of two almost squares in the denominator? If I think of 2 as the square of the square root of 2, then we're dealing with an arctangent here. So the antiderivative, remember, 1 over a is simply the square root of my constant term, 1 over a, arc or inverse tangent of x over a. And we're going to need to evaluate this from 0 to 1. Now, the second integral we can't handle directly, but we can make a u substitution. Do you recognize what the u substitution should be? We're going to let u equal x squared plus 2. du then is 2x dx. That's going to cover the numerator, but let's multiply both sides by 1/2. So this becomes plus the integral of, now I'm changing variables. I'm going to put stars here so that I can go back and recover my original x. I don't want to plug 0 and 1 in for u. We can rewrite this as u to the negative 2, that's 1 over u squared, times 1/2 du. So again, I'm going to postpone evaluating this first term. I'll do them all at once when they're ready. So I'm just going to copy that term down. Now we can integrate. We're going to have 1/2. We're going to end up, when we integrate, u to the -1 over -1. Let's go ahead and rewrite that as -1 over 2 times u. And again, this is a definite integral, but I don't want to use 0 and 1 for u. So on the next step, we'll recover x. We're getting closer. Hang in there. Almost there. Now we have -1 over 2 times our original u, which was x squared plus 2. Now that everything's in terms of x, we can go ahead and apply our limits of integration to the entire expression. So plugging in first our upper limit of 1, we have 1 over the square root of 2 times arctangent of 1 over the square root of 2. Plugging 1 in for x, 1 squared plus 2 is 3. So that's what our antiderivative looks like evaluated at the upper limit. Let's go ahead and plug in our lower limit of 0. We can call this arctangent of 0. Plugging 0 in for x, again we have 2 times 2. Now notice that first term, arctangent of 1 over square root of 2, it's really tempting to call that pi over 4 because you associate at least square root of 2 over 2 with the angle pi over 4, but tangent of pi over 4 is 1. So that right there is an exact value, and that's the best that I can do. So I'm going to leave it as arctangent of 1 over square root of 2. You can rationalize it or you can leave it. Over here we have arctangent of 0, which of course is the angle 0. And last here, be careful to distribute your negative. We have minus a negative or plus 1/4. So I'm just going to combine those two fractions with a common denominator. -1/6, let's see, common denominator of 12, that'd be -2/12 plus 3/12. So how about plus 1/12? That is an exact value. We could certainly approximate that with our calculator, but we have successfully evaluated the integral. So as you look over your work, the big idea is, how do I set up those partial fractions? Are the factors linear or quadratic? Are they unique or repeated? If you have a linear denominator, you assign a constant numerator. If you have a quadratic denominator, you assign a linear numerator. Also, we looked at two methods for how to find those undetermined coefficient. In one case, we were choosing convenient x values, zeros of the factors. And in another case, we were setting coefficients of the polynomial on the left equal to the polynomial on the right. Even after you separate your integrand into partial fractions, you still have to be prepared to use a variety of integration techniques that we've learned up to this point. So you are accumulating a lot of skills. Hang in there, keep practicing, and don't give up.